Well, this is a tricky little problem, and it's really interesting, I think. Here's the picture that you can see that shows somewhat realistically the biceps muscle, the bones, the cannonball, everything that's going on here. I'm going to draw it in a much less interesting way. I'm just going to draw the bones of the lower arm represented just like that. Now I'm going to draw in the forces where they're applied. So the first thing I'm going to draw in is the cannonball. So that's going to be a force pointing downward right here at the end of the hand. I'm going to call that mass of the cannonball times gravity. The next thing I'm going to put in is the mass, the weight from the mass of the arm itself. And so right here, right in the middle of the arm, I'm going to put an mg representing the weight of the arm. So that's going to be mass of the arm times gravity. So those are the two forces that are holding it down. There are also two forces holding it up. First of all, there's the force from the bone. So let's call that F sub B, the bone holding this up. And that's applied right here at the joint, right there. There's the force from the bone. And there's one more force. It's the force from the biceps muscle. And the biceps muscle is attached here, inside on the arm. And it's also pulling straight up. So I'm going to call that F sub N, the force from the muscle. So we have a total of 4 forces happening, and this is where they're working. We can, first of all, write a force balancing equation. And remember, a force balancing equation, we just add up all the forces on one side, and then that's going to be equal to 0 because this is something that's not moving. So I've got 2 upward forces, force from the bone and force from the muscle, and 2 downward forces, one from the weight of the arm and the other from the weight of the cannonball. Okay, so those are all of my forces, and those add up to 0. Well, in the 2 parts of this problem, we have to find the force from the bone and the force from the muscle. And this one equation is not enough to find both of those. So we need to do another equation, and the only way to get another equation is from torques. So let's go back to our diagram and draw in lever arms for torques. Now, we can consider any axis of rotation that we want to. And the torques are always going to add up to 0. But the axis of rotation I'm going to choose is the most obvious one, the one where it is actually going to rotate, and that would be around the elbow joint. So that's going to be my axis of rotation, and I'm going to take my lever arms from there. So first of all, the lever arm for the bone force is 0. That means that the bone force isn't going to exert any torque, which is great. That'll keep it out of the equation. So next we go to the muscle. And the muscle has a lever arm that looks like this. So I can call that R subscript M for lever arm for the muscle force. Then the next lever arm will go to where the weight of the arm is being applied. That's at the center of mass of the arm, halfway from the elbow to the end. So this lever arm here is going to be R sub A, because it goes with M sub A, and that's going to be half the length of the arm. And then our last lever arm goes from here all the way out to the cannonball. This one, we can call this R sub C, the lever arm for the cannonball force, and that's going to be the whole length of the arm. So now we've got all of our lever arms. Yay! Now let's look at all of our angles. The angle between this lever arm and that force is 90 degrees, so we don't have to worry about that. This one, also 90. This one, also 90. So we don't have to worry about any lever arms. So let's write our torque balancing equation. We're going to add up the total torque and set that equal to 0 because nothing's moving. So first I'll do the muscle force, and its torque is R sub M F sub m. And then there's the torque from the weight of the arm, so that would be R sub A, M sub A, G. And then there's the weight of the cannonball causing a torque, that would be R sub C, M sub C, G. And we know this is going to add up to 0. But we need to stop to think about what's positive and what's negative. It looks to me like we have two forces causing torques that would tend to make the arm go downward, and only the muscle force is pulling upward. If we want to call that positive, we want to make this force positive, then both of these have to be negative. But it's just important that these two weight torques are the opposite sign from the muscle torque because they're working in opposite directions. So from this equation, you should be able to get the answer for part A. Because what you're looking for in part A is this, the force from the muscle, and you know everything else in here. Then you go on to part B. And to do part B, you're going to use this equation. Bone force plus muscle force minus the two weights has to equal 0. We knew that from force balancing. We now have the muscle force, so we can plug that in. We know everything else in here, so we should be able to solve it.